Hello, my name is Sekiyama, Division of Materials Physics, Graduate School of Engineering Science, Osaka University, Japan. In this movie, the optical property of solids is explained from the infrared to X-ray region based on microscopic interaction between the incident light and charged particles, electron in solids in most cases. Then, the universal nature of the high frequency limit of the complex refractive index is explained. Please enjoy this movie.
From here, as the first realistic example, I explain the energy or frequency dependence of the dielectric function. Crystalline solid, of which the optical properties we discuss are made of atoms which are often in ionized state. Even when there are ions in solids, their charges are cancelled out by the other ion with opposite sign or electrons, and total charges is neutral in a macroscopic scale. Since the interaction between the incident light and the charged particle in solids are microscopic and taking place locally, the optical properties characteristic of the materials are seen in macroscopically charged neutral solids. We can notice that interaction between the incident light and solids are divided into three ones. One is interaction between the light and ions, which is predominant for insulators, especially important for ionic crystals in the infrared range. Another is the interaction between the light and free electrons or conduction electrons, which is predominant for metals in infrared, visible light, and sometimes also UV regions. In atoms or ions, there are many inner core and valence electrons with a number of nearly their atomic number large Z, which are rather strongly bound to their nuclei compared with free mobile conduction electrons. In the high energy region, such inner core or valence electrons also interact with the incident light. Therefore, we also need to consider the interaction between the light and inner core electron to understand the optical property of all materials, irrespective of metals or insulator. In this lecture, I explained the second one, term 2, the interaction between the light and free electron in solid and its consequence. Let me start to explain the dielectric function for free electron gas based on the Drude model. We consider one electron in solids interacting with the incident light, whose electric field is expressed by this formula. Here the light is supposed to be linearly polarized along the x direction, where the propagation direction is along the +3 direction. This electron in solid experiences the force by the electric field of the incident light. So, the equation of motion for this electron is expressed like this. The first term stands for the Coulomb force by the electric field. The second term represents the effect of inelastic scattering of this electron by the lattice of solids. If the electric field is static and electrons are kind of steady state even under the static field, the problem becomes a situation of obtaining DC conductivity or resistivity of solids. In this case, however, the electric field is no longer static, so we need to solve this differential equation. Here, we consider the large X tilde times exponential function as a candidate of the solution for this equation, where the large X tilde stands for the amplitude of the electron oscillation. When we substitute this for small x in the equation motion displayed here, this relation is obtained. After the simple calculation, we obtain the solution of the large X tilde proportional to the amplitude of the applied electric field of the light as a function of angular frequency omega of the incident light. Next, we obtain polarization by the electron oscillation given by the incident light. According to the classical electromagnetism, the polarization vector P is the density of induced dipole moment. The obtained large X tilde represents the displacement amplitude of this electron by the incident light. Therefore, the induced dipole moment by this electron is expressed as -e times small x in the above equation of motion. When we define the electron density as small ne, then the polarization vector P is obtained as this form. Rigorously, this formula, including the exponential function, is correct. The applied electric field is along the x direction. The large X tilde has been obtained as this form, as explained before. Therefore, the polarization of the solid with the free electron density of small ne is obtained as this form. Here, this part is equivalent to the electric field value by the light, which means that the polarization is proportional to the applied electric field as seen in electromagnetism. So, this part corresponds to the coefficient giving the electric susceptibility of chi tilde. From here, I omit the exponential function to save the space. Then the polarization is also expressed as this form. The electric susceptibility chi tilde is thus expressed as this form. Here, omega p is defined by this formula, which is called as the plasma frequency of the solid. As explained later, this quantity can be directly estimated from the energy dependence of the reflectance. Since the dielectric function is expressed as 1 plus chi tilde, the dielectric function is expressed as this formula. We notice that real part is an even function of angular frequency omega, while the imaginary part is odd with respect to omega. These are consistent with the nature of electric susceptibility as explained before. On the other hand, the imaginary part of the epsilon2 is also represented by using the optical conductivity shown here. Therefore, the optical conductivity is also obtained as this form. Here, the numerator in this formula is equivalent to the DC conductivity. The optical conductivity is of course related to the DC conductivity, which is one of the most important quantities in metals. Ideally, the optical conductivity approaches to the DC conductivity on going to omega of 0. Therefore, we can know the DC conductivity as the extrapolation of the optical conductivity at omega of 0, which can be probed by the infrared and visible light spectroscopy even if we do not measure the DC conductivity. This model explained here is called as Drude model. Here I show the simulation result of the Drude model reflecting the realistic material aluminum. Aluminum has a face-centered cubic crystal structure with a lattice constant A of 0.405 nanometers, where there are 3 nearly free electrons per atom. According to the DC measurement, the static conductivity is obtained as of the order of 10 to 7 ohm inverse meter inverse, corresponding to the law of 10 to minus 8 ohm meter. From these quantities, we can obtain value of small ne and tau in advance like this. The carrier density is of the order of 10 to 29 inverse cubic meters, while tau is of the order of femtosecond. When we put the electron mass as a normal value, then we obtain the practical formula of plasmon frequency or plasmon energy. Plasmon energy is proportional to the plasma frequency as a function of the free electron density small ne as shown here. For aluminum, we can evaluate the plasmon energy of 15.8 electron volt from the calculation, which is very much higher than the energy of h bar over tau, less than 100 milli-electron volt. When the plasmon energy is much higher than the h bar over tau, the electric function is expressed as an approximated form like this one. Then the photon energy is higher than the h bar over tau but lower than the plasmon energy. Epsilon 1 is less than 0. That means it takes a negative value, and its absolute value is much larger than that of epsilon 2. This behavior is schematically shown, displayed in the figure. Then the real part of the refractive index n is obtained, followed by this formula. In this case, the square root of epsilon 1 square plus epsilon 2 square is approximately obtained as this formula. N is nearly the same as epsilon 2 over 2 square root of minus epsilon 1. Since the imaginary part kappa is rigorously obtained as epsilon 2 over 2n, which is evaluated as a square root of minus epsilon 1. This value is much larger than n, because the absolute value of epsilon 1 is much larger than epsilon 2. This is also schematically shown in this figure. Now we can evaluate the normal reflectance from n and kappa. Here kappa is much larger than n. The normal reflectance is nearly 1 when the incident photon energy is lower than the plasmon energy as shown in this figure. The reflectance decreases rapidly when the photon energy exceeds the plasmon energy here. This photon energy dependence of the normal reflectance is completely consistent with our experience, namely the fact that the aluminum will reflect the incident light, which is more or less common to conventional metals. Practically, we can know the normal reflectance from the experiment. For that of metals, the sudden drop of the reflectance is seen in the photon energy dependent measurement ongoing to higher photon energies, which can recognize as a plasma edge. Then we can estimate the carrier density small ne by using the free electron mass. Sometimes the carrier density small ne has been obtained from the other experiments, such as the measurement of the Hall coefficient, or carrier density can be estimated from the expected number of free electrons from the crystal structure. In such a case, we can estimate the effective electron mass m star from the plasma edge from this practical formula. For some materials, the obtained effective mass would be heavier than the free electron mass, reflecting the electronic structure of solid or electron correlation effect. When the effective mass becomes heavier, the plasma edge is lowered. For the conventional metals, the color of the surface is usually not black, since the plasma edge is on the visible light or VUV region. However, it is known that the highly conducting transition metal oxides show the black color. It is due to the lower carrier density than that of the conventional metals, and often due to the electron correlation effect, leading to the heavy effective electron mass, where the m star over m is larger than 1. This picture shows the surface of the high-temperature Q-plate superconductor, lanthanum strontium copper oxide, with nearly optimally doped. You can recognize that the color of the surface is surely black, which indicates that the plasma H bar omega p, is in the infrared region. For such materials, the photon energy H bar omega in the visible light region is already higher than the plasma H, and therefore the reflectance of many visible light components is lowered, namely they are not reflected, and then the surface color becomes black. The left graph shows a comparison of the normal reflectance calculated by the Drude model by solid line with the experimentally obtained data for the conventional metals aluminum and silver by the dashed line. For aluminum, the calculation of the plasma edge itself when we produce the experiment. On the other hand, the numerical deviation in the reflectance is seen as shown in the figure. This is due to the effect of so-called interband transition of aluminum, which suggests that the conduction electrons are not completely free electron-like, but supplied from the 3sp orbital band, of which the orbital character remains a little bit. For silver with the FCC crystal structure, the carrier density expected from the lattice constant and electron per atom leads to the plasma edge of about 9 electron volt. However, the drop in the reflectance is already seen at the photon energy of around 4 electron volt in the experiment. This inconsistency between the calculation and experiment is due to the fact that the experimentally observed drop in the reflectance is not from the plasma edge, but due to the interband transition from the fully occupied 4D to unoccupied 5sp conduction band. In the visible light region of the photon energy from 1.5 to 3 electron volt, the reflectance is experimentally higher for silver than for aluminum. This is not only for the normal reflectance, but also for the all incident angle as shown in the right figure, in which the incident angle dependence of the reflectance at the photon energy of 2 electron volt corresponding to the wavelength of 620 nanometers. For silver, the reflectance is more than 90%, even at the Brewster angle in the p-polarization. This is due to the fact that the kappa is much larger than 1 and the n is much smaller than 1. In a daily life, the silver coating is normally used for looking glasses, called as mirror. As I talked, the interaction between incident light and solids are mainly divided into the interaction between the ions, interaction between the light and free electron in solid, which has been explained, and interaction between the light and inner core, including valence electrons. I start term 1, namely the interaction between the light and ion in solid. In other words, the light and lattice in crystal. So, as I said, I have explained term 2, interaction between the light and free electron, representing the conduction electron in solid, mainly applied for metal. Now, then I showed the effect of term 3, interaction between the core and valence electron and light, which must be applied for all materials, irrespective of metal or insulator or semiconductor. So let me start the explanation of the interaction between the light and ion in solid. According to the Drude model describing the interaction between the light and free electron in solid, there is no carrier in insulator. That means the insulator must be transparent for the light. That is incorrect. So we need to consider the effect of the lattice vibration or lattice oscillation. So this view graph stands for the schematic picture of the interaction between the light and ion. Since the ion has a charge, they can interact with incident light. At the same manner for the explanation in the Drude model in the last lecture, the light is expressed by the time-dependent electric field as shown here. Here we suppose that the mass of ion as large M and charge of the ion as small q. Then the equation of motion for ion is expressed by using this formula. Here the minus kx stands for the so-called restraining force of the spring. In the lattice, the ion is set on equilibrium position. If the ion is slightly moved in any direction, the ion tends to move to backwards. So in this case, the ion in lattice can be expressed by using the material bound by the spring. So this minus kx stands for such a force. The second term stands for the damping term of vibration once the lattice starts to oscillate, but in future such kind of oscillation is damped. And third term stands for the force applied on ion by the electric field of the light. So this is the equation of motion for ion. Then we need to solve this equation. So here I set the solution as large x tilde ion times exponential function for small x. Then we obtained this condition. So this can be obtained by the calculation of the derivative of these terms. Then we need to obtain large x ion by using the other quantity. Then we get this result. Large x tilde ion is proportional to the amplitude of the electric field of the light. Here, omega 0 square is defined by the small k over m. So this is the solution. Then we can consider the polarization of the ion. Here I introduced large N as ion density. Then the polarization of ion due to the incident light can be expressed by using this formula. Therefore, the polarization is also proportional to the amplitude of the electric field of the light. Then we can define chi-tilde ion, charge susceptibility of ion. When we compare these terms, then we can notice that chi-tilde ion is expressed by using this one. When we remind that the electric function is expressed as 1 plus chi-tilde, if there is no conduction electron in the material, when we consider only the lattice oscillation by the light, we get the electric function of such a material as this form. Then I continue the explanation of the dielectric function of lattice or harmonic oscillators. So this formula can also be expressed like this. So here, this part is a real part and this part is an imaginary part. You can also notice that the real part is an even function with respect to omega, while the imaginary part is odd function with respect to omega. The frequency dependence or photon-energy dependence of this dielectric function is drawn in this graph. I also show the complex refractive index obtained by the square root of the epsilon tilde, like this one. Please pay attention to this term, imaginary part. You can notice that when the omega is nearly omega 0, this one becomes 0, the imaginary part becomes larger and larger. So then we can notice that the imaginary part of the dielectric function epsilon 2 takes a peak at omega of omega 0, like this one. So the change of the real part epsilon 1 is larger around omega 0. Accordingly, the imaginary part of the refractive index shows nearly maximum at the omega of 0. So the next problem is the energy scale of this peak. This is omega 0. When we compare omega 0 and omega p plasma frequency explained in the last lecture on the Drude model, the omega p is of the order of several electron volts in the visible or ultraviolet region. On the other hand, this phenomenon is seen in the infrared region because of the factor of the large m, mass of ion. Plasma frequency is related to the electron mass. Therefore, we need to compare the ratio of the electron mass and ion mass. Plasma frequency is inversely proportional to the square root of electron mass. Therefore, we need to compare the square root of small me electron mass over large M. This value is of the order of 1 over 100, 0.01 or something like that. So omega p is in the energy scale of the electron volt. Omega 0 is in the scale of the few tens to 100 milli-electron volt. This is completely in the infrared region. And I discussed the effect of the absorption. So kappa stands for the degree of the absorption. That means the absorption of the light becomes stronger at the omega of omega 0. This formula tells us that the infrared light can be absorbed by the ion. On the other hand, lattice oscillation can be expressed by the concept of phonon. Phonon energy scale is of the order of the few tens to 100 milli-electron volt. That means this Lorentz model is a problem of the interaction between the light and phonons. Further, we take the fact that the temperature stands for the degree of the lattice oscillation solid. The enhancement of the lattice vibration by the infrared leads to the increase of temperature. So please remember, in the hot summer day with the sunshine, there is a glass made of silicon dioxide. When you touch the glass, you feel the glass is very, very hot. That is due to the absorption of the infrared light by the glass. That means the glass is transparent for visible light with a photon-energy of 1.5 to 3 electron volt, but strongly absorb the infrared light. Another importance is that epsilon 1 is larger than 1, even at omega of 0. That means even in the static field, there is a finite polarization in the ion according to the Lorentz model. This leads to the polarization at the DC electric field of material, mainly for ions. That is the explanation of the Lorentz model. Then I start the explanation of the interaction between the incident light and inner core or valence electron in solid. As you know, the inner core electron strongly bound to nuclei, and valence electrons in solids are described by using the quantum mechanics. Therefore, we need to consider the quantum mechanics for electrons. For simplicity, here we consider one electron Hamiltonian expressed by using this famous formula. This term stands for the kinetic energy and this term stands for the potential. And we assume that we have already solved this Schrödinger equation and obtained eigenfunction phi n and eigenenergy En. And further, we suppose that the electron is in the ground state with the eigenenergy of Ei and wave function of phi I before photoabsorption. This phenomenon, absorption of light by inner core or valence electron, is described by the time-dependent perturbation theory of quantum mechanics within the semi-classical theory, where the electrons are treated by using the quantum mechanics, but the incident light itself is expressed by the externally applied electric field, classical electric field. So we consider time-dependent perturbation theory divided before and after irradiation. Starting time of the light irradiation is time of 0. Further, it is assumed that wavelength lambda of the incident light is much longer than the displacement of the electron position expressed as small r. Of course, the electron can move, but the degree of the moving is much shorter than the wavelength of incident light. In such a case, we can use so-called long-wavelength approximation. In order to discuss the time-dependent perturbation theory, additional potential made by the incident light must be real number. So here we consider the incident light electric field as this function, cosine function. Then we applied long wavelength approximation, whereas lambda is much longer than r. X is a component of vector r. Here we suppose that the electric field is along the z direction and propagation direction is along the x direction. Then the wave number or wave vector is along the x direction. Since k is inversely proportional to lambda, amount of kx can be treated as negligible owing to the long wavelength approximation. Then we can express the electric field as this form. Further, we can expand the cosine function as this formula. In this case, the we can approximate the electric field is position independent due to the long wavelength approximation. Then we try to solve the time-dependent perturbation. In the static field theory, electric field is minus of the gradient of the potential. Therefore, the additional potential can be expressed by using this formula. Therefore, the additional potential which should be added to the original Hamiltonian is expressed as this formula. The problem is the Hamiltonian before irradiation is expressed only using the electron Hamiltonian He, but after irradiation, Hamiltonian must be expressed as He plus V prime. V prime stands for the interaction between the incident light and the electron. Then we consider the Schrödinger equation, time-dependent Schrödinger equation after irradiation, namely at the T is positive. So this is the exact form of the Schrödinger equation. Then the solution of the time-dependent wave function psi is expressed by the linear combination of the eigenfunction phi n, which has been obtained as a solution of electron Hamiltonian He. Time-dependent wave function can be expressed by using this formula, the linear combination of the function phi n. Then the problem is how to obtain the information of the coefficient an. Of course, before irradiation, the electronic state is in the ground state described by the one electron wave function phi I. Therefore, psi is equal to phi I at time of 0, just starting time of the irradiation. In this case, coefficient ai is 1 at the t of 0, and other coefficients a is 0 at time of 0. Then we put this formula into here and here. This is a result of the expansion. Then we consider this relation. We can notice that these terms are cancelled out. Then we obtain this differential equation. By solving this differential equation, we obtain the coefficient an. But it is very difficult to perfectly solve this differential equation. We pay attention. Coefficient ai is nearly 1, slightly smaller than 1. Of course, other coefficient an should be finite, but very, very smaller than that of ai. So, situation is like follows. Light is radiated, but very small portion of the electron can be excited. All other electron is still in the ground state. Therefore, the probability of the transition is far from 1, very small. With considering this fact, we continue to solve this equation. At first, we consider one eigenfunction phi f. This is a final state wave function of the electron. Of course, both these and these functions are mutually orthonormal when we multiply the phi f star conjugate of the phi f from the left-hand side of this differential equation. The left-hand side term is finite only for the AF dot. Then we get this equation. Then we consider this situation, namely the state is slightly changed from the state before irradiation. only small portion of the electron is excited. That means AI square is still nearly 1, less than 1. Other coefficient, square of the other coefficient is finite but very very small and negligible. I forget to say that this term is moved like this one by multiplying the exponential function. Then we continue the calculation. As I said, we assume that this condition, then we can use the approximation, and we obtained this result. So that means only we consider the state phi I in the right hand side terms, since the other coefficient is much smaller than the coefficient AI, and AI is nearly 1, we obtained this approximated result. We can analytically calculate this integral. Then we obtain this result. And further little bit complicated calculation, we obtain this one. And finally we get this result. This one is another expression of the integral. Importance is z in here. Of course, in the product of the state f and state I is 0, but z in here, result of the integral, can be non-zero, finite. H bar omega fi stands for the energy difference between the final state and initial state. This energy difference stands for the h bar omega fi. More or less, we get the solution of this differential equation by using the approximation. Then we go back to the polarization. For the positive time after starting the irradiation, the time-dependent wave function of the electron is expressed by using this formula. AF is much smaller than 1. In such a situation, we can estimate induced polarization by this electron. According to the definition, the mean value of the dipole moment is obtained by the integral of this one. Wave function is expressed by using this formula, and this term is very small compared with the first term. Then the terms of this one can be neglected. Then we obtain the charge polarization by the incident light expressed by using this formula. We remember the coefficient AF is expressed by using this one, which is shown in the previous slide. We put this one into here and here. The formula becomes longer. We find some terms can be cancelled out, like this. Then finally we get this result. I explain every term. First term stands for the so-called spontaneous polarization. Here there's no terms of electric field. That means this term means polarization without light. Therefore the spontaneous polarization. If the crystal has a space inversion symmetry, since Z is odd, this term becomes 0. The spontaneous polarization can be seen only for the system breaking the space inversion symmetry. And this term is proportional to the electric field of the incident light, since this is E cosine omega t. So this term represents a dipole moment proportional to the applied electric field. And third term, the time dependence is omega Fi. This is an oscillation independent of the frequency of the electric field of the incident light omega, time average of this term becomes 0. So I'd like to say that this one is the coefficient of the polarization proportional to the applied electric field. Therefore, when we consider this coefficient, we obtain the charge susceptibility of electron. So then we consider the charge susceptibility. The large V stands for the volume of the atom. Since the polarization is also expressed by the dipole moment density of solid, then the polarization vector can be expressed by using this formula. Then we can estimate the charge susceptibility. Further, we consider the fact that the excited electrons are no longer stable. Therefore, once the electrons are excited in the high energy level, such an electron fall again. That means the transition of the excited electron to the lower state takes place within a short time. So we include this effect into the lifetime of the core hole tau I. Electrons are excited and core hole is yielded due to the photoabsorption. Then we get this formula as a charge susceptibility. This one is almost similar to this one, but the effect of the lifetime of core hole is added here. Then we see this formula again. This one and h bar omega fi are independent of omega, angular frequency of the incident light. Chi tilde I, this is a charge susceptibility of one inner core electron, as very similar to that for the Lorentz model as this one, which is described in previous slide. Okay? This is a constant with respect to omega and very exactly same omega dependence as this one. Therefore, the real part of the chi tilde is still finite even when the omega of 0, which leads to the contribution of the polarization of the inner core electron even at omega of 0. For many insulating material, the real part of the complex refractive index is larger than 1, as shown here. This is due to this effect. So this is a result of the interaction between the incident light and inner core or valence electrons bound to nuclei. Then we can discuss the effect of the interval transition of the insulator or semiconductor. The valence electron is more or less has a similar character of the inner core electron. Inner core electron is described by the wave function of hydrogen-like atom. So the valence band electron can be expressed by the linear combination of the orbital wave function. Therefore, even for the valence band, more or less bound to nuclei has a similar nature to that of the inner core electron with respect to the interaction with photon or interaction with incident light. So this view graph stands for the schematical energy diagram of the valence band and conduction band. So usually the valence band energy is below the film level, and for the insulator or semiconductor their band gap is Z. Since within the gap there is no density of state, photoabsorption due to the interband transition must be seen when the incident light photon energy h nu is larger than the band gap Eg. So therefore, for the insulator or semiconductor, even for the metal, finite effect of the dielectric function epsilon tilde at the photon energy larger than the band gap. On the other hand, the visible light photon energy is from the 1.5 to 3 electron volt. That means the transparent insulator have a band gap is larger than the 3 electron volt. Then I discuss another thing about the momentum. Photon momentum is estimated as h bar omega over c. In this case, the photon energy is at most 20 electron volt for the valence band. Usually it's a few to several electron volt, but maximum value is supposed as 20 electron volt, corresponding to the minimum wavelength of 600 angstrom. Then we can evaluate the wave number inversely proportional to the wavelength of incident light as 10 to minus second angstrom inverse. On the other hand, this is a problem of the solid-state physics. The band electron momentum is of the order of the brilliant zone size. A stands for the lattice constant, then pi over A can be evaluated as of the order of 1 angstrom inverse. Compared with this and this, we can notice that the band electron momentum or band electron wave number is much larger than the photon wave number or photon momentum. This is a schematic drawing of the band dispersion of the valence band and conduction band. Horizontal axis stands for the electron momentum or electron wave number. In this photoabsorption, since photon momentum is much smaller, electron is excited with keeping the momentum. So this is a direct transition. So direct transition is the transition holding the momentum conservation law. On the other hand, we can also observe the indirect transition with different electron momentum between the initial and final state. But in order to see such phenomenon, the assistance of phonon, in other words, assistance of the lattice oscillation is mandatory. Therefore, the intensity itself is weak compared with the direct transition. So this is explanation of the interband transition due to the incident light. So in order to understand the interband transition, we need to consider the interaction between the incident light and valence electron by using the time-dependent perturbation theory. So by now, we consider one electron in solid interaction between the incident light and electron. But in reality, in order to obtain the charge susceptibility of the material, the contribution from the electrons, we need to add all contribution of all inner core and valence electron. Therefore, the electron contribution except for the free electron, the charge susceptibility is summarized by using this formula. Here, we need to add all excited state F. So the calculation is very complicated, but we can understand many things from this formula. When the photon energy is much smaller than all energy difference omega Fi, a real part of the charge susceptibility is positive. For most insulators, the real part of the refractive index is larger than 1, because the real part of the dielectric function is larger than 1. Okay? For the visible light region, photon energy is of the order of 1 or 2 electron volt, and energy difference is much larger than that value, then real part of the refractive index n, small n, must be larger than 1. Then we consider the opposite situation. The photon energy is much higher than energy difference. This situation is in the hard X-ray region. In this case, we can neglect this term compared with h bar omega because we consider this situation. Then we can discriminate the omega dependence part and omega Fi dependence part like this by using the approximation. And further, we assume that 1 over tau is much smaller than omega, since the energy scale of the lifetime is of the order of 100 milli-electron volt, which is much smaller than the incident photon energy. Then the charge susceptibility of each electron is approximately expressed by using this formula. Then we consider the fact that for this term, the sum rule can be applied like this, very simple form. Then the charge susceptibility of each inner core electron can be expressed by using this formula in the high energy limit. Then we can evaluate the high energy limit of dielectric function for material. As I explained in the last lecture, according to the Drude model, the conduction electron contribution to the charge susceptibility is like this. This is also the approximated form. Each core and valence electron, the charge susceptibility is expressed by using this one. And when we see both formulas mutually similar. For the ion, based on the Lorentz model, form is rather similar, but this value itself is negligible compared with the electron contribution because the mass of ion is much heavier than the mass of electron. And this should be Me. Sorry. Okay? In the high energy limit, we can neglect this term. Of course, this is important in the infrared region, very small omega region. But high energy region, only electron contribution is important. Then we can get the total charge susceptibility of material by using the total electron density large Ne as this form. This is a real part of the charge susceptibility of material in the high energy limit. On the other hand, for the imaginary part is much smaller because we consider the situation where omega is higher, h bar omega is higher. Then epsilon tilde dielectric function is expressed by using this one, whereas the imaginary part is much smaller than the real part. Okay, so this can be understood since contribution from the conduction electron, the imaginary part is much smaller than the real part, and also for the inner core and valence electrons, the imaginary part is much smaller than the real part. Then we get this form. In such a situation, the real part of the refractive index is simply expressed as square root of epsilon tilde. Then we get this result. And further, the second term, this term is smaller than 1 in the high energy limit. We obtained approximated form as this one. So this one tells us that real part of the refractive index is slightly less than 1. Almost nearly 1, but slightly less than 1. On the other hand, imaginary part of the refractive index is proportional to the total electron density large Ne and inversely proportional to the omega cube. you know that lead is employed for the stopper of gamma ray because lead is heavier atom and also has a large total electron density because atomic number is much larger than 1 and I don't remember, around 80 or something like that. So lead can stop gamma ray due to the large total electron density, large Ne. Okay. Importance is that irrespective of metal or insulator, in the high energy limit, the refractive index has a similar tendency, namely in the X-ray region, except for the absorption edge, the real part of the refractive index is nearly 1, but slightly less than 1. And imaginary part kappa is much smaller than 1. This is a consequence of the interaction between the incident light and charge in solid. Charge means mostly electron, but including the ion. But ion contribution is negligible in the high energy region such as X-ray or gamma ray.